We talked about some exponential equations in another video, but I wanted to review that so that we can do more advanced ones and ones that have logs in them. So if we have something like this, 16 to the 3x power equals 8, and we have to solve for x, we could experiment and probably figure out some of these just by looking at them, but sometimes they're going to be harder, and what we want to do is find a common base. If we can find a common base, we can get somewhere with this. And so I know that 2 to some power gives me 16, and it happens to be the 4th power. So I'm replacing the 16 with a 2 to the 4th. And then I still have a 3x power on all of that. And then I'm going to replace the 8 with a 2 to the 3rd power, because that would make 8. So what that does is you can use the power to a power. So one base to two exponents, you can multiply those exponents and get 12x. And then this is just 2 to the 3rd. And if the bases are the same and they're saying that this thing is equal, then the exponents have to be the same as well. So you can just say, well, that means 12x would have to equal 3. That's the only way that would be equal. So we're going to solve for x by dividing both sides by 12. And so x would equal 1/4. And that's what would go right here to make those two things equal. You can always check your answers to see if that actually works. You could take 3 times 1/4 is 3/4. Take 16 to the 3/4 on your calculator and see if you get an 8. So that method works great when you can find common bases. But what if you can't find common bases? There is not a common base that we can raise both of these to. And so we have to have another method. And this is where logs have a great use. If you take log of both sides, you'll be able to use one of the log rules to get the x out of the exponent. It's one of the only ways you can get x out of the exponent. And so what we're going to do is we're going to take the log of each side, because doing the same thing on both sides, just like sometimes we square rooted both sides or we cubed both sides, we did all kinds of things to both sides. Well, we can take the log of both sides, and that is an okay operation. So now let's see what happens. What that causes is it immediately causes the x to come out of the exponent and get to a place where we can work with it. So that exponent rule of logs says that you can pull the 3x in front of the log, multiply it by the log, and then the 15 will no longer have an exponent on it. And then we'll leave the other side the same. Well, now this looks like something that we can work with, because we can get this x by itself. It's connected to both the 3 and the log 15 with multiplication. So we can divide the 3 out and the log of 15 out, and we can divide them out at the same time. And then do the same thing on the other side to balance it out, so that the 3's reduce out and the log 15's reduce out, and we just end up with x on this side. And this side we can do on the calculator, but be careful, because if you don't group the top and bottom in parentheses, it's going to turn out wrong. And the reason is because it will think that you're just doing log of 285 divided by 3 and then multiplying that answer by a log 15, which means it's kind of grouping it like this automatically if you don't tell it any other grouping in particular. So to make that log 15 be on the bottom of the fraction as well, you have to group the denominator, and you might as well group the numerator. It's always a good idea if you have a complicated numerator or denominator to go ahead and group it anyways. And then you may have an automatic opening of parentheses here, and if you do, make sure you close that one before you close the numerator one. And same with the 15. You may have one that automatically opens for the log 15, and then you want to go ahead and close that one before you close the denominator parentheses. So you're going to put this in exactly like it looks in the calculator with a dividing symbol where the bar is. So rounding it off to 4 decimal places in this case, we get this answer. Now you could always check it by going all the way back up to the beginning, put in 0.6 0.958, which is an approximation. It's not going to come out exact. Put that next to the 3 in your exponent, 15 to that power. And then you won't get exactly 285 because we did round this number. So you'll get approximately 285, but if it's really close to 285, you should know that that was probably the right answer. One use of logs to help us find the missing exponent is an example we've done before with exponential growth or decay. So let's talk about money. Let's say we start out with $1,000 and we're wanting to know how long it's going to take for it to increase to $5,000 when we have it in an account that makes 6.5% interest and we're missing the time. That's what we're looking for, is how many years. So let's put it in for the final amount is 5,000. The starting amount was 1,000. The interest rate, it's increasing, so it's 1 plus, and it's 1 plus 0.065, and 1 plus that is 1.065. And then t is the thing that's missing. So let's see how long it takes. Well, with t in the exponent, you could use the graphing method and find the intersection of the graph to the x-axis. But you can also use logs now that we understand logs, because that also gets that t out of the exponent. So what I would do first is divide both sides by 1,000 so you just have the exponent portion left. And when you divide both sides by 1,000, you get 5 on the left side and you get just the 1.065 to the t power on the right side. So to get the t out of the exponent, we can use logs now. So we're going to take our equation and take the log of both sides. Now you could take the ln of both sides just as well. Your calculator will find either one. And what that does when you find the log of both sides, or take the log of both sides, it allows us to be able to move the t down in front as a multiplication to the log of 1.065. That gets it out of the exponent, which is what is taking log of both sides is useful for. Then we're trying to solve for t, so we would divide both sides by log of 1.065. Divide by log of 1.065. These cancel each other out, and you end up with t equals whatever this is on the calculator using your log button. When I did that on my calculator, I got approximately this, which, if we're talking about years, it'll be about 25.5 years before you go from 1,000 to 5,000. And you can say 25.5, or you might have to say 26 years if you round properly to the whole number. It just depends what kind of preciseness they require. So that is how you get an exponent variable out of the exponent so that you can solve for that exponent. If you need to solve a problem that already has log on one side, probably the easiest way to do that would be to write in what the base is if it wasn't there already. And so this one had a base of 10. Use your definition of log to rewrite it as 10 to the second equals 4x minus 3. And then you'll be able to solve for x just with normal solving methods. And you get x equals 25.75, and that was not rounded off, so I'll go ahead and leave it as a decimal. If it were needing to be rounded off, you might want to leave it as 103/4 as a fraction. Here's one that has two logs in it on one side and then no logs on the other side. You wouldn't want to take logs of both sides or anything like that. You can just try to see if you can get all this as one log, and then that might allow you to use the definition of log to get it out of logs altogether and into exponents instead. So this is why knowing how to go from 2 logs down to 1 log is a useful property. So we are going to say that this is log of x minus 3 times x, and that equals 1 still. So we just used one of our properties of logs to say that 2 logs separately added is the same as 1 log with those 2 things multiplied. And then what we can do is, since we have a single log now, we can use the definition of log. This has a base of 10. So we can say 10 to the first power equals I'm going to put the x in front, all that stuff. So it's that same stuff that was in the brackets before, just rearranged. And then we can solve this. We've got methods to solve this. So this is 10. This is x squared minus 3x. As soon as you see that there's an x squared in the problem, you're probably going to want to get everything on one side equal to 0 so that you can factor or use the quadratic formula. So I subtracted 10 on both sides to get a 0 on this left side. That leaves us with a quadratic equation that can be solved either by factoring our quadratic formula, and I believe this one will factor, so we'll come up here and factor it. Then set each factor equal to 0 and solve each one, getting x equals 5 and x equals negative 2. You will want to check both of these answers because it turns out that the negative 2 one does not work, not necessarily because it's a negative 2 and not a positive, but it just doesn't work when you plug it back in to see if this plus this will equal 1. It does not work, but the 5 does work, and so that is the solution to this particular equation.